Hello and welcome to our brief video explaining atomic instructions and how they relate to operating systems. First, what are atomic instructions? Atomic instructions are hardware instructions that perform an operation on one or more memory locations atomically. Basically, we do some group of actions all at once as one uninterruptible action. Why do we care about atomic instructions? What purpose do they serve? In operating systems, multiple processes sometimes need to use and make changes to the same piece of data at the same time. This can be dangerous and cause what is called the race condition. Let's explain why this is dangerous and how atomic instructions solve it.
So to illustrate what does the atomic instructions mean, we wanted to talk about a scenario of a tic-tac-toe game. Now, a tic-tac-toe game will not entirely describe very precisely what does atomic instructions mean. Our goal here is to simplify the idea of atomic instructions to make it very possible to understand by everybody. So the first scenario will be the very cause why we need atomic instructions. What problem do we have that we need to come up with instructions to overcome that such problem? And the name of that problem is race conditions. Race conditions is pretty much a race. Two processes, or could be more processes, at the same time racing to make a change on the same thing at the same time. So in this scenario, let's talk about race condition. Let's assume player X plays first, okay? So what happens is that here's the table, okay? Now player X gets the table, it wants to make a change on it, but at the same time process 2 gets the table. Now at the same time process 2 gets the table. Now process 1 places an X here, okay? And then while process 1 placed an X there, process 2, let's say process 2 wants to place an O here. So when process 1 updates it, the new table in the terms of player X is going to look like that. And when player O updates it, in the terms of process 2, the table will look like this. Okay. Now we see that they're different, and these two processes will not be able to play the game like this for sure, because there is no synchronization. They're not synchronizing the data here. They are not really playing on the same game board. The game board is here. They need to update the very same table, but they're in the terms of creating their own instances about it. So this is the race condition. Two processes or more are making a change on a variable, could be at the same time or one after the other. The idea is that they're not synchronized. Now let's talk about atomic instructions. Okay, so let's assume again player X goes first. Goes there, picks up the table. The game board is here. And let's assume it wants to place an X there. So while process 1 is doing this in the terms of getting the game board and placing an X, if player O, process 2, wants to make a change for it and tries for it, it cannot, because it's not supposed to. Because it's supposed to wait process 1 to be completed. Once process 1 is completed, then process 2 can go in and make that change. So once process done is completed, X, process 2 gets the table, okay, player O gets the table with an X here. Now this changes the scenario because process 1, if it tries, it will not be allowed. So once the process 2 is done with the making change, then it updates the table. The goal is to find a solution to a race condition that we really talked about right here. If two processes wants to update the table, they need to wait their turns. Like here. Process 1 get the table, update the table. If process 2 attempts to get the table while process 1 is making a change on it, it will not be allowed. And once process 1 is done, updates the table, process 2 can change the table with its own value.
Now we're going to go over some examples of multi-instruction methods used as one uninterruptible instruction. The following examples help us avoid that pesky race condition we just talked about. The first is fetch and add, which solves our incrementation problem. Fetch and add increments the value of a specific memory location by a given value. The operating system and all processes see this as one atomic instruction and no race condition occurs. The second is compare and swap. Compare and swap compares the value at a memory location with a given value and only makes changes to the memory location if the value at the memory location and the given value are the same. Otherwise, no change is made. That'll conclude our video on atomic instructions and how it relates to operating systems. Thanks for watching.